We're now going to take a look at free energy and the connection to the equilibrium constant, K. So, under any conditions, standard or non-standard, and we discussed what standard meant, there were some conditions that were met, 1 molar concentration, 1 atmosphere pressure, things of that nature, when delta G naught was measured. So this is our standard delta G here. But even under non-standard conditions, we can solve by using this other term here, which includes the gas constant, R. Notice the units are different than when we calculated PV equals nRT, things like that. These units are now, instead of liter atmosphere, we have joule per mole Kelvin. So slightly different units because we have energy that we're talking about now instead of pressure, volume, temperature, things like that. But we will also multiply by temperature, T in Kelvin, always in Kelvin. Notice Kelvin might cancel out here. And then we have this other term here, the natural log of Q, which is our reaction quotient. And we should note that if we have standard conditions, this second term will actually cancel out, and we'll see that our natural log of Q would equal 0 when we have 1 molar standard condition. So no matter what our products divided by our reactants would be, no matter what the exponents are, anytime we have 1 times 1 times 1, we would always end up with a natural log of Q equal to 1, which if you plug that in your calculator, you would see that the natural log of 1 equals 0. So 0 times 0 times 0, that's why this term would cancel out under standard conditions. And we can generate this simplified form of the equation. We'll talk about both of these equations when we do some calculations, whether we're under standard state or standard conditions or not. So let's look at this sample exercise 10 here and see if we can calculate delta G. And notice we're at 298, so we're going to be at standard conditions here. And we are given some information. I apologize, we're not at standard conditions here. We're given our values here to plug in and calculate our Q. So that wasn't meant to be a trapezoid, but we got everything in there that we needed. So let's calculate, or at least write the equation for a Q here. It's always going to be the same kind of relationship as K. And if you recall, our equilibrium constant was always our either concentration or pressure of our products raised to whatever stoichiometric coefficient divided by our reactants to their coefficient. And that's the same for if it was pressure, right? We would just put it in regular parentheses instead of brackets. So we have concentration or pressure. So K, equilibrium of concentration or pressure. Same thing with Q. We're going to put products over reactants. So we have the pressure of our sole product here, pressure of NH3, and we're going to have to remember to square that. And then in our denominator, we'll have our reactant, so N2 to the first power, right? We don't need to write anything there. And then H2 is cubed. So let's plug in some of these values right here to solve for our Q. So we'll have on top 2.0 squared, and then on the bottom I have 0.5 for my nitrogen. That's not raised to any power besides 1. So we can just write that as is, and then 0.75 cubed for my H2 because there's a 3 coefficient. So we plug all this in and we solve, and we should get 18.96. This is my Q value. And now if I want to solve for my delta G non-standard, I'll take my delta G naught, my standard conditions here, put that first, and then to that I'm going to add, remember that's RT ln Q, so 8.314 times 10 to the negative third, and I'm going to put that there because our unit is given in joules, but I want to combine that with kilojoules here. So I'm just going to divide by 1,000 or multiply by 10 to the negative 3. And then I have to plug in my temperature. So that's why temperature is always given, 298 K. And we'll multiply these values together. And then we have to add to our equation, the ln Q as well. And I forgot to divide by Kelvin. Kilojoules per mole Kelvin are our full units here. And then if we plug in that 18.96 over here, we'll take the natural log of that, multiply by 298, multiply by 314 to the negative third, and then we'll combine like terms. So both of these will end up being in kilojoules when Kelvin cancels. And we should find that we end up solving for delta G as negative 26 kilojoules per mole. And this would indicate a spontaneous reaction the same way as when we solved for delta G naught or delta G at standard conditions. So let's take a look at one other problem here. But first, let me introduce one more set of equations here. So I mentioned how under standard conditions, we assume 1 molar concentration. So Q is 1, and then the natural log of Q is 0. So we saw that this term here dropped out, or will drop out when we are under standard state. So let's see some other relationships here. Then Q would be equal to K, the equilibrium constant. And we saw in an earlier video that our delta G is equal to 0, again, at equilibrium. So what happens is our equation simplifies again. We have at equilibrium a value of 0 for delta G, so that's over here. And then our standard conditions plus RT ln K now. So now that we have this new equation, we can rearrange it and get this form here. And then if needed, we can rearrange this form to solve for K. So that's what we're going to do in this problem here. So sample exercise 11, we're asked to calculate, or using the value of delta G, we're asked to calculate our equilibrium constant. So we're going to solve for K. And we're given our temperature 25 C. So let's take a look here what values we're going to plug in. Actually, first let's write out that rearranged form. K equals E. So you'll have to locate the E button on your calculator, and then you'll raise that to delta G naught, whatever value you're given, divided by RT. So remember that's negative delta G naught. So if we're given a negative value, that will actually be positive when we take the negative of that. And also, since our R value is in joules per mole Kelvin, we can either change that by dividing it by 1,000, or we can multiply our delta G to convert that to joules. So let's multiply by 1,000 and let's plug in those values and solve for K. So I'm going to put E raised to, I'm going to write it nice and big, negative 33,300 joules per mole. And then in my denominator here, I'll have R, so 8.314 joules per mole K, times our temperature in Kelvin. So to 275, I'm going to add 273, so that's about 298 Kelvin. All right, I'll plug everything in. So usually I'll solve for all this. So positive 33,300 divided by 8.314 times 298. I'm going to get that K is equal to E raised to the 13.45. So I'm going to plug that in, and I find that to be, if I keep a few digits, 6.87. times 10 to the fifth. This is a very large K. So we can say that when K is greater than 1, delta G, right, we saw that was negative, and this reaction would be spontaneous. And if we have the contrary here, if K is less than 1, we could probably assume delta G to be positive, and then that would be non-spontaneous. So the remainder of this video, we'll talk about a different equation. We'll introduce that, and actually we'll introduce a couple equations here. So first we can think about a linear plot equation of the natural log of the equilibrium constant versus 1 over temperature, and of course that would be in Kelvin. So if we took a plot of this, this would give us a straight line plot or a linear plot. So that's good to know. That might come up later. Let's look at this equation as well. So this is called the Van Hoff equation, and this can be used to relate these K values, like the one we calculated above, these constants, such that, say, we have K2 divided by K1. If we had our enthalpy value for whatever phase change, whatever we're talking about, we're given a delta H for the reaction. We can divide that by R, that same gas law constant. And then in this form, we'll have 1 over T to the first power. So the first temperature that goes with the first K value here, and then minus 1 over T2, which that will go with that corresponding K value there. So this again is called the Van Hoff equation. And we can also introduce one other equation here called the Clausius-Clapeyron equation. And this relates pressure values. So similarly, if I have the natural log of P2 over P1, I can relate that ratio to, say, an enthalpy of vaporization, divide that by the gas law constant, the same one, 8.314 joules per mole Kelvin, and then times 1 over T1 minus 1 over T2. So just keep these equations in mind. This is sometimes used in biochemistry. This specific equation would be for a liquid to gas phase change. So we'll continue with the next topic in the next video.